the first slide,
There we go.
as the first slide says, this is part 2 of the perception series, a short one this time that I started a few weeks ago, right after the new year, on perception. And this time I'm going to talk about interoception, and in particular proprioception, as opposed to the external senses. So these are the internal senses and how we make use of them. And now let's see why I can't get this stupid thing to advance. There we go. All right, so interoception is a very old term, and it's developing modern meanings in both psychology and physiology. And when I talk about new, actually psychology is leading the way, and most of the research associated with interoception only started in the 2000s, and the earliest literature citation that I could find was in about 2003, and it was in psychology. But both disciplines have essentially the same idea. They're how we perceive the state of our body. And in psychology, it's becoming extremely important, and I've listed a bunch of references down there. But basically, it's become the basis in psychology for what we call self-awareness and the emotions associated with them. And the flip side of that is that misinterpretation of those same body signals that give us self-awareness compared to what the body thinks or the brain thinks of as its normal model is the source of abnormal emotional states like anxiety or PTSD. And I'm not going to talk any more about the psychological side of it, although I keep running into it all the time, because in physiology, it's a much newer term. And if we look at a 2013 neurology textbook, as you'd expect, the textbook is focused on nerves, and especially the nerves of the somatosensory system. And if you remember from part 1, that's the sense of touch, essentially. And the book starts out describing the pioneering work of Sherrington that led to an understanding of various ways muscles and nerves communicate with the brain through electrophysiological signals. And he won the Nobel Prize for that in 1932. But that textbook, even though it's very modern, defines proprioception very broadly, pretty much the way the psychologists do, as a sense of oneself, self-awareness. And it limits exteroception to just touch. And so it's talking about an external sense as if it's an internal sense in the context I'm going to use it. And it defines interoception even more narrowly. It says basically the visceral system, how the body unconsciously regulates its own organs. And so that's, you know, like almost less than 10 years ago, which is pretty wild. Well, I'm going to use a much more modern definition of interoception. It's pretty much like the psychologists, how we perceive ourselves. But in physiology, it's not a very common term yet. And the vocabulary and the definitions of that vocabulary are still in a state of flux. But I'm going to use it as how our internal senses tell us about and control our bodies. And there are really 2 parts to it that I'm going to talk about. And it's very difficult to define them without examples, but non-conscious perception is how the body responds to external stimuli like pain and losing one's balance, while conscious is how we respond to those stimuli, both internal and external, like needing to go to the bathroom or pain for that matter. And the visceral system is still part of non-conscious proprioception, but I'm not going to talk about it this time. And so proprioception is what I'm going to focus on. And it's basically been called the sixth sense. And its actual focus is how we perceive the position and motion of our body in space, which seems like a simple proposition, but I can assure you that it's not. So there's two parts, and trying to explain non-conscious is best done by examples. It's body awareness. If you raise your arm over your head, you still know where it is without looking at it. Or you do all kinds of activities without thinking, like chewing and swallowing and running, or walking upstairs in the dark. And so non-conscious proprioception is the basis for all of that kind of activity. While conscious proprioception uses a lot of the same information, but it's associated first with execution, conscious decision-making. I want to grab an egg. And then the refinement of that movement of grabbing. How hard should I squeeze before I know I'm going to break it? And there are terms that describe a lot of the associated aspects of those kinds of proprioception. There's muscle memory or kinesthesis, which is really storing repetitive motions in a part of the brain so that we don't have to think about using them in the future. And then there's a couple associated with the sense of touch. Taphonosis, the ability to know where touch occurs, like if somebody touches us, we don't have to look at where that touch is coming from. We know it's coming from our arm or from our nose or our head or something like that. And then haptic perception is the more common term. And that's the ability to recognize the shape of an object just by touching it, again, without looking at it. And please, nobody give me the example of the blind man and the elephant. This is not what that's all about. And then there's finally somasthesia, which is an awareness of feelings in your body. And it's really a term that's been co-opted from psychology, but it's when you know your leg doesn't feel quite right, or your stomach doesn't feel quite right, and you're not sure how you know it, but you're sure you know that. And so that's another aspect of proprioception. So it covers a wide range of activities and phenomena. And basically, I'm going to show it to you in two parts. I'm going to show you how it works, and then I'm going to show you some of the simpler things you can do with it, especially non-conscious proprioception. And I'm going to leave conscious proprioception and movement associated with conscious decision-making to next time, as well as the anatomy associated with that kind of movement. So the proprioceptive system is how the movement portion of interoception works. And there's two components, or four components, since I can't count already this late at night. There's skin receptors, so that's the same sense of touch I talked about last time. And I'm going to talk about it again, but I'm going to talk about it from a different perspective. And I'm going to talk about some of those same skin receptors also from a different perspective and in much more detail. There are the proprioceptors themselves, the receptors in our tendons, in our joints, and in our muscles that feed information to the brain. There are the special nerve pathways, and I'm going to be talking about the afferent ones that provide information from all of those receptors to the brain. And then I'm going to talk about the parts of the brain associated with using that information in a non-conscious way. I mean, you'll see it called unconscious, but we really are awake when it's happening. So I don't like the term unconscious. I use non-conscious instead. And the two parts I'm going to talk about in particular are the somatosensory cortex, that's part of the cerebral cortex, and the cerebellum, where the cerebellum is called the little brain, which is literally what that means. So skin receptors, and you've seen a picture sort of like the one on the left in part one. That's what skin looks like. And we've got a lot of it, at least 20,000 square feet for the average person. That's a lot. And I'm going to only talk about 5. I meant 20, not 20,000. I think that's what I said. But in any event, it's a lot, but not that much. And I'm going to only talk about 5 of the receptors that are really the ones associated with proprioception. There's a couple of others that I mentioned last time, but I'm going to ignore them because while hair follicles and Krauss bulbs really can play a role in all of this, they're really very unimportant in the greater scheme of things. And the schematic on the right basically shows an example of what they look like and where they are, but I'm going to go into more detail. So the first ones are, and I'm going to go sort of from the top of the skin to the bottom of the skin as I talk about these. And the first one is called the Merkel complex, and really it's the Merkel cell, the top part of the complex, that's the business end of all of this. It's really tiny. It's a little round disc, literally only about 10 micrometers in diameter. And it's got fingers associated with the top of it that stick into the cells of the epidermis. And so it's really stuck to the epidermis tightly. And so it can't move around within the skin layer. And the disc is just a synaptic nerve ending that's paired with the Merkel cell. So each very small area of skin, and I didn't try to define what that area is, but that area only contains a few of the Merkel cells. And the axons from the discs on all of the cells in that small area all connect, as you can see on the left in that yellow, to one big primary nerve. So it's basically an array, a touch array over that small area. And it's a real, it's got real signal transduction. So it's a real pressure receptor in the classical sense. I'm not going to go into the details, but you can see them over on the right. If you distort the top disc by pressing on it, it opens and closes various kinds of ion channels and eventually releases a neurotransmitter that goes across the synapse to the Merkel disc. And the interesting thing about it is that as long as you put the pressure on, the signal keeps going until obviously the disc or the cell runs out of juice. But it takes a long time. And so it's a very slow response to sustained pressure. And it's a very localized touch because of the small area associated with this Merkel cell array. And so that's the kind of touch we use to define the edges of objects and ultimately their shapes. Now the Meissner corpuscles in the next level down, and it's really in the upper layer of the dermis, the second layer, but it projects up into the epidermis in a papilla, just like we talked about the bumps on our tongue when we were talking about taste in part one. So it's a very similar structure. And it's a mechanoreceptor, but it doesn't have any signal transduction associated with it. It's just a modified nerve ending. And it's much bigger. It's elliptical, and it doesn't have a very big diameter, but it's really long. So it sticks up really far into the epidermis. And basically what it is a single branched nerve with lots of terminal ends. And those terminal ends are stuck in between a bunch of flattened cells that are parallel to the surface of the skin. And pressure causes the cells in that corpuscle to slide past one another. That distorts the terminal nerve ends. That depolarizes those ends and produces a signal. And that signal eventually is collected after it goes across a synapse, like in the previous receptor. Now, in this case, if you maintain the pressure, the signal disappears. So it's a very rapid response to a very light touch and low frequency vibration. And it gives you the sense of localized movement over the skin. Like if you rub your finger over the back of your hand, you can feel that. And the slower you do it, the higher the sensation is that you get from that sense of touch. The next one is even bigger. It's 1 millimeter long, and you can actually see these suckers with the naked eye. Now it's ellipsoid as well, and it lays parallel to the skin surface instead of sticking up. And it's also a modified nerve ending. And it also sends its signal along by synaptic transfer. And in this case, very special synaptic transfer. So it's not true transduction either. And in this case, what you have is a naked nerve ending that sticks out in a cavity into the middle of this layered onion-like in cross-section kind of encapsulated set of cells. And it's got gel associated with it that sort of damps out the pressure response from touch. And so what happens is if you push, that distorts the membrane, and you can see in the bottom picture something called the note of Ranvier. That's the synapse between the nerve that's the extension of that naked end and the rest of the nerve system going into the rest of the spinal cord and eventually up to the brain. So this is one that responds really rapidly to transient touch as opposed to the one that responded slowly, but not to steady pressure. And it's sensitive to really high frequency vibrations, the kind that creates a tickling sensation in your skin. And you can try all of these things because it's easier to see what I'm talking about by doing it as an example than actually me trying to explain it. And then there's this beast. This is found everywhere in the body and also in other tissues, as I'll describe. And it's at the highest density at the ends of fingertips. And I'll give you the punchline first. It's most important for control of finger position and movement. And so for feedback, when we try to grip an object, or for piano playing and a whole bunch of other things for non-conscious proprioception. And it's located at the interface between the dermis and the layer that we don't normally talk about, the hypodermis. And that region is composed of collagen fibers for the most part. And so one end of this capsule and the fibers that are in it, which are collagen fibers, connects to either end of the normal collagen fibers that make up that interface. And it's, again, got one nerve with a bunch of branches and a bunch of nerve endings. and they're all tangled up in these collagen fibers. And so when you stretch the skin by putting a lot of pressure on it, you get a continuous nerve signal for as long as that pressure is maintained. But it's a very delocalized kind of touch response and a very slow one. So we've got all of these different kinds of response times, and you'll see how that plays out when I start talking about the next piece in a few seconds here. And then finally, you've all seen free nerve endings from the previous talk that I gave on the skin. And it's very dense in all skin, about 1,000 of these ends per square inch. And it's also all over the place in the body, free nerve endings. But most importantly for this talk, they're in skeletal muscles and they're in joints in particular. And you can see in the diagram that there are two different kinds of endings. There are ones that end in the dermis, and then there's ones that go all the way up to the top and project into the very upper layers of the epidermis. And so we have varying levels of sensitivity in those nerve endings. And one of the phenomena that's associated with these different kind of nerve endings is what happens in damage. Because like if you burn your finger, the epidermal layer is the one that usually gets burned, and all of those little tiny nerve endings get burned off. And so you get an immediate zotch from the initial pain of the burn, but then it goes away. And the reason it goes away is because you've essentially removed those particular nerves in that particular area out of play. You've still got the other ones, and so you can still detect pain and you can still detect temperatures, but it's a much slower process because of that. And this time, when I started talking about the different kinds of nerves associated with these nerve endings, I've talked about what's really key to how they operate, whether they're myelinated and how thickly they're myelinated. And I'll talk more about that in a few minutes. But first, let's talk about the proprioceptors, the actual motion receptors, if you wish. And I've listed them in the order of complexity and for a couple of other reasons, but that's the main one. I'm going to get you into them gradually because they get more and more messy as I go. And so first we have the Golgi tendon organ. And for those of you who don't know that much about anatomy, your tendons connect your muscles to your bones. And so that's why the muscles work, because they're attached to your skeleton. And when the muscle moves, your skeleton moves. So the tendon organ is actually a group of encapsulated collagen fibers, which is what the tendon is made out of. All right, and at one end, that group of collagen fibers is connected in series with muscle fibers, and at the other end, it merges into the normal fibers of the tendon itself. Now, again, this is a big organ. It's about 1 millimeter long, but it's really, really, really skinny. It's only 1/10 of a millimeter in diameter by comparison to the millimeter. So it's a 10-to-1 ratio. And the nerve is very large and it's myelinated. And so again, I'm not going to go into all the details, but as the muscle contracts, the collagen bundle stretches, that squeezes the terminals from the branched nerve, that opens a cation channel at the axon synapse, and that connects the axon from the tendon organ to what is called the primary or first order nerve. And now we're starting to talk about how the signal goes from all of these receptors into the spinal column and eventually up to the various parts of the brain where it's needed. So the signal is proportional to the tension in the tendon, and it produces a feeling or a sense of force. It's like when you press your hand against the wall. Nothing moves, but you know the muscle is working, right? You know it's exerting a force on the wall, even though there's no motion in the muscle itself. And the signal is strongest when the muscle is actually moving, when it's actually, for example, lifting a heavy load. And then we get to the joint receptors. And again, picture of the joint over on the left. And the part that we're most interested in is what's called the joint capsule, where the cartilage that lubricates the two bones that make up the joint are situated. But there's also a fluid in there, which is really why it has to be encapsulated so strongly. And all of a sudden, what we're looking at are basically the touch receptors I just described, the Ruffini endings, and they're in the outer portions of that joint capsule. They're in the membranes, the pisciform corpuscles, and very similar, the Golgi-Mazzoni corpuscles. And they both are pretty much the same, and they're in the inner joints, in the inner layers of the joint capsule. So we've got some on the outer side of that membrane and some on the inner side of that membrane. And then we've got the Golgi organs again, and they're in the tendons close to the joint capsule, and they're actually in the ligaments as well, but not very many of them. And then we've also got free nerve endings in the joint capsule and in the ligaments. So all the receptors that we saw for touch, but they're the ones that make up the receptors that are part of the joint receptors. And those receptors respond to a change in the angle of the joint. They respond to a change in the direction. And that is usually something like a rotational torque. Like if you turn your arm sideways rather than just opening or closing it. And it's also sensitive to the velocity at which the joint moves. So all of these receptors are looking at three different properties of the joint. And if you'll remember, each of these different kinds of receptors that we just talked about has a different kind of nerve associated with it. And you'll see more of that in a minute. And so there's lots of different kinds of information that's going to travel up the spinal column to the brain, all at different rates or velocities through those nerves. Now we get to the muscle spindles, and these are a mess. And I've used 3 pictures and they still don't explain it all. And I've simplified the description, and that still doesn't explain it all. And I've given a lot of detail. But again, what we have is a capsule, and this time it's a capsule of what look like muscle fibers, but they're not. They're special kind of muscle fibers. Regular muscle fibers are called extrafusal. Don't ask. The ones in the capsule are called intrafusal. And there's 3 kinds of intrafusal ones. And for some reason or other, they're called bag 1, bag 2, and chain. And so usually they're just B1 and B2. And the number depends on the size of the spindle that we're talking about, because these spindles are embedded in the middle of all of the skeletal muscles, as well as the muscles of the back and the neck and the jaw and all sorts of other places, with the only exception being the facial muscles, the muscles above the mouth. Those are moved and provide information in a totally different way than all of the rest of the muscles in the body. And we're only talking about external muscles, not something like a heart muscle, for example, or some of the other muscles in the internal organs that we have. All right, so the most important thing is that there's 2 different types of nerves that are coiled around each of these intrafusal special muscle fibers within the spindle. We've got B1 and B2 intrafusals, and each of those has a group 1A nerve, and that nerve detects the rate of change of the length associated with that spindle stretching. So it's looking at a velocity. The group 2 nerves are attached to those intrafusal fibers at a slightly different place. They're attached near the ends of the capsule, while the other one is attached near the middle. And they've all got funny names like annulospiral and flower spray, but none of that really matters unless you're trying to understand this stuff. And those smaller nerves have a slower response, and they are the ones that detect the change in the length of the muscle spindle or the length of the nerve itself. And both of those nerve types send what are called afferent signals, signals going from the receptors to the brain via the central nervous system. And so the other thing associated with muscle spindles is that those same muscle fibers have nerves around them that are responsible for initiating muscle movement. I mean, there's no down to the touch receptors. They just provide signals going to the brain, right? But for muscle spindles in particular, everything else is passive. The muscle spindles are active. And so there's alpha neurons and beta neurons that are attached at different ends of the muscle fibers, and the nerves associated with them are called fusomotor, and they're the ones that receive information, signals from the brain, and tell the muscle to do something. And so the alpha and the betas are attached to the muscle fibers themselves, and the betas and the gammas, and there are 2 types of gammas, are attached to the intrafusal muscles of the muscle spindle itself. Now, you don't have to really remember all of that. It's just that there's different kinds of nerves that transfer information at different speeds from the spindles to the brain, and there's different kind of nerves that have different speeds associated with the information coming from the brain back to the muscle spindle. So now let's talk about the nerves. And here you can see the different types of nerves that I'm talking about. You can see that the muscle spindle nerves, at least the one type, the group 1A, the ones that need a very fast response, are very thickly myelinated and have a huge conduction velocity, somewhere around 100 meters per second. So that signal travels like a bat out of hell, right? The other ones that are associated with the length change are also fast, but they're group 2. And those nerve fibers actually transmit signals fast, but not as fast, even though you can't see 2 different kinds on the chart. And the tendon organ has thickly myelinated, and they're group 2, but they're a class A alpha, as opposed to a class 1 alpha. And so they have a fast response because they're myelinated, but the response isn't as fast as either of the nerves associated with the muscle spindles. And this will all start to make sense when you see what happens to these nerve signals. And then you have joint receptor and touch receptors, and all of those have a thin coating of myelination, but they're sort of medium fast. In fact, they're sort of slow, somewhere between, on the average, of about 50 and 20. So they're right sort of in the middle between those 2. And then finally, you have the nociceptors for pain and temperature. And again, there's 2 kinds. the thinly myelinated, remember I pointed those out, and the non-myelinated. And so you have slow responses and very slow responses from those kinds of receptors. Now it starts to get complicated. And the first time I gave a talk like this, it ended up being basically a neuroanatomy lesson, a very long one. And I never really was able to make the point or focus the talk on the objectives that I wanted to, because I was trying to give too much detail. So I'm just going to sort of gloss over a lot of this stuff and wave my hands, but you'll get the idea of what's going on. So we were talking about primary axons. The nerves from the receptors themselves go through a synapse and connect to a primary nerve. That primary nerve eventually combines with primary nerves from other kinds of receptors that are all associated with a particular part of the body. And that because that nerve bundle is protected, and the individual nerve fibers in that bundle are much less likely to get damaged. So that's a protective mechanism. And then that big fat nerve bundle goes through something called dorsal root ganglion, even though, again, the terminology on the diagram is posterior root ganglion. And that's just the way it goes. Like I said, more than one name for everything. I call them dorsal root, which most people that aren't nerve anatomists also call them. So anyhow, that acts like a big sorting center, and it resorts all of the those primary nerves that came from all of the different kinds of receptors, and sends them to the proper place in the center of the spinal column. Right here, you've got basically this disc, and it's got outer parts, and it's got that funny looking shape in the middle. And again, you got to remember that everything I'm talking about, even though I might show it for only one side of the body, everything is symmetric. And one of the weird things you can see is that some of the nerves, like for pain and temperature, they cross from one side of the body to the other when they get to that disc. Some of the others don't, they just go straight in and up. All right, so that acts as a sorting center, and it sends each of the nerve types from each of the receptors to what's called a spinal cord tract. And I'm going to try not to use two words, tract and pathway, interchangeably, because they're really two different things. One is a position in the spinal column. The other is actually the pathway that the signal takes within the spinal column from its starting point until it reaches the brain. So the nerves eventually enter the spinal cord through the appropriate dorsal root ganglion and get sent to what's called the central horn of that disc. And that acts again as a sorting center. And you can see that it's got somatic and visceral, and there's also information for motor, all in that horn. And all of those are very sophisticated sorting centers. They're not just synapses of one nerve into the big nerve that's going to go up the spinal cord. They're much more sophisticated than that, as I'll show you. And again, if you look over here on the left, you can see all of the different discs and the various nerves that are associated with those regions, where you can remember that the two major areas where all of these nerves are coming from are from the cervical nerves, the neck and shoulders and arms, and more importantly, from the lumbar and sacral region. And the other thing to remember when you look at this diagram is you've got all of these discs running up the spinal column. And some of the discs from the neck don't go all the way down to the bottom and then back up again. They just go straight across and join along the way. And so you've got long pathways and short pathways, even though they're all carrying the same kinds of information in the same area, and they're all going to the same part of the brain. And just to give you some idea of how all of this stuff is organized in tracts, here are the kinds of tracts sort of in gross detail. This is gross detail. And so you've got what's called the dorsal column tract, and it's got a lot more names associated with it. And it carries some of the proprioceptor information and most of the touch information, and it eventually goes up to the cerebral cortex, the thinking part of the brain. And then you've got two spinothalamic tracts, and they carry the pain and temperature information, and they also go to the cerebral cortex. And then you've got two spinocerebellar tracts, and that's where most of the proprioceptor information goes. And that stops at the cerebellum, not the cerebral cortex. And so that's sort of the organization. And one of the things to point out is that dorsal column tract, you can see that it's sort of divided up. And even in this crude diagram, you can see that there's a sort of a turquoise region for the upper body and the blue region for the lower body. And if I look at even more detail, here you can see on the left that that part, the dorsal column, is divided up: neck, arm, upper trunk, lower trunk, and leg. And so all of the location information is actually maintained in the spinal column itself. It's not just one giant bundle of nerves sort of randomly going up to the brain. It's all very neatly and precisely sorted out from bottom to top. And if you look over at the right, you can see that each of these tract areas that I was talking about is not just a simple area. You can look at one of these, like the spinothalamic tract over at the right side, and it's got spino-olivary, tectal, as well as just spinothalamic. And each of those small regions is associated with the information going up there. And part of the reason that there's so many different divisions is where those nerves are meeting that disc, whether it's from the upper part of the body or the middle or the bottom part of the body. All right, now we're going to talk about the pathways themselves. And the somatosensory, the pathways leading from all of the touch kind of receptors, go through the thalamus to the cerebral cortex. And in fact, where they go is a part of the cerebral cortex called the postcentral gyrus. Now, there are only two neurons in the entire pathway from the, say it's coming from the leg, from the very bottom of the spinal cord until it gets to the thalamus that sends it to the right part of the brain. There are only two nerves. The one that goes from the primary, that goes from the axon of the receptor through the dorsal ganglion to the horn, and then one that goes from the horn all the way up non-stop to the thalamus. And that's a big nerve. And so you get very rapid transmission of the signal to the cerebral cortex because the body needs a rapid response to some touch inputs, like severe pain, as an example. You don't want to wait around for the signal to reach your brain before you react to it. And here's the postcentral gyrus, and I hope people can see the sculpture on the right, because that's the fun part of my talk. The postcentral gyrus, for those of you, again, who are brain anatomists, you would call it the Brockman area 3. And here again, we've got all these multiple names for the same thing. So it's located in the lateral parietal lobe, right sort of in the middle of the brain. And it's symmetric, it's got two sides. And some of the information from the left side goes to the right side and vice versa. And some of it doesn't, but it's all touch information. But the important thing is if you look at a cross section through that postcentral gyrus, what you see is that all of the location information from the origin of that touch information is maintained in that slice of cortex or in that slice of cerebral cortex. And so what you end up with is a map that can be illustrated in what's called a homunculus, that little figure on the right. And you can see it in 2 dimensions laying on the top of that slice, but it's much more interesting in 3 dimensions where you can really see the proportions, because basically what the homunculus is saying is that there are more nerves in our hands and in our mouth and tongue, and many fewer in the rest of the body. And so that part of the homunculus is outsized. And basically, the part of the body in the diagram or the sculpture is proportional to the number of nerves providing that kind of information to that part of the body. And so the homunculus becomes a mnemonic for trying to remember some of that information. And homunculi are used for a number of these anatomical features in the brain. Okay, so now let's talk about the proprioceptors. All of that stuff was for most of the touch information. And so now what we're looking at, if you look on the left, is the spinocerebellar tracts. Instead of going to the cerebral cortex, the central gyrus, all of this information is going to the cerebellum. And so there's one first order neuron that goes from the receptor, not dopsoral, but dorsal root ganglion. So again, the information goes through that dorsal root ganglion, but then there's only one nerve that goes all the way up the spinal column directly to the cerebellum. There is no third order nerve. And that's a very, very fast nerve. It's either, for the most part, one of those class 1, type 1 or type 2, or maybe a type 2A or something like that. But they're all very fast. And that information is used for non-conscious proprioception, especially what we're calling body awareness, all of those tingly feelings and things I was talking about, and non-voluntary movement. Now, I've simplified all of it in this description, and then I'm going to complicate it again, because as I showed you, the ascending pathways are much more complex than I illustrated them to be. And if I go back 2 slides and you look over here at the green portion of the dorsal column at the bottom, you can see that there's a whole bunch of different shades of green. So those are all of the different pathways that end up at the medulla and then get sorted out by the medulla and go to the thalamus and eventually into that post-lateral gyrus. And so for the proprioceptors, you got to remember that the muscle spindles have two different kinds of nerves that travel at two different speeds. And some of the info ascends via that dorsal column, and some of it goes up via this part. And the joints have all different kinds of receptors with nerves that travel at different speeds. And so this is much, much more complex than the simplified way I laid it out. And on top of that, even though it's still an active area of study, we're still not sure what the pathways are for touch. What kind of touch goes up the spinal column, how? Because some of it doesn't go all the way to that post-lateral gyrus. Some of it ends up in the cerebellum because the cerebellum needs it for non-voluntary movement. And so this is a really, really oversimplified overview of the anatomy of all of this stuff. But that's not the important part. That's the part I simplified so we can talk about the guts of the talk here. So first I got to talk a little bit about the cerebellum, the little brain, and it's got really two parts that we're interested in. If you look over on the left and you see the red arrow, the first part are called the peduncles. And the peduncles are where all of the input for the proprioceptors and some of the touch stuff goes really fast up to the cerebellum, right? But first it goes through the peduncles, and the peduncles act as traffic cops. They sort out the information because just like the cerebral cortex has parts that do different things, the cerebellar cortex, that part that's sticking out, also has parts that do different things. But what's it all used for? The information that goes to the cerebellar cortex is used in what are called reflex responses. It's where the repetitive proprioceptive tasks that are called muscle memory are stored. And it's also used for a mouthful that doesn't make any sense on the face of it: non-conscious initiation of conscious movement. I'll explain it, but not this time. I'll explain that in part 3 when we talk about movement and how that works. And then some of the information, after it's gone into the peduncles, gets passed on to two different organisms on the way to the cerebral cortex. The red nucleus and the thalamus. And if you can follow the pathways to and from the cerebellum, you can see where that information goes and how it eventually ends up, again, at the upper part of a slice of the cerebral cortex, some of it going to the somatosensory gyrus and some of it going to the motor cortex. So even that is complicated. And on to what all of this is good for. So one of the most important aspects of non-conscious proprioception are what we call reflexes. Those are involuntary, nearly instantaneous movements in response to a stimulus. Like I said, we step on a tack, we don't want to have to think about, should I lift my foot or not? We feel the pain as fast as possible because stepping on a tack is bad, and we pull our foot away as fast as we can, and we don't make a decision to do it. It's all done involuntarily, non-consciously, and all of that is controlled at most for complicated reflexes by the cerebellum, but even before the information gets to the cerebellum. And so there's all different kinds of reflexes. There's primitive ones. Babies are born with 5 basic ones and are actually tested to see if they have those kinds of reflexes, because that tells the pediatrician that the nerve system in the newborn baby is probably okay. And doing those tests are a real quick way to determine, at least for the gross part of the nervous system, that it is intact and working properly. And then you get the kind of what are called myotactic reflexes, like when you go to the doctor's office and one of the things he does is he bangs your kneecap and you have a knee jerk. Well, there's a whole bunch of those. There's actually 9 basic ones for all the different parts of the body. And again, basically what the physician is doing is he's testing to see if the first connection between the receptors and your spinal column are intact. And so that's what doing all of these tests for the different parts of the body are all about. And then there's really complex kinds of reflexes, and they protect the body from injury. Like if we've got something in our eye and the touch receptors know it's there, blinking, which causes the tear ducts to operate, is a protective mechanism. And so is sneezing if we get something in our nose that doesn't belong there, or gagging or coughing. So that's a fairly simple reflex. And then the hot stove reflex, where we touch something or we step on a tack and we pull away the limb. That's a very complex reflex. And I'll talk about these kinds in more detail. And then there's something called the conditioned reflex. So muscle memory is really a conditioned reflex. It operates under the same basic principles that these other ones do, especially the complex reflex. So it's acquired through experience. You do the same thing over and over again. You practice the same piano piece. You hit a ball 1,000 times. You whack a tennis ball with a racket 1,000 times. And all of that proprioceptive information, the motion information associated with the proprioceptive receptors in particular, gets stored in the cerebellum, in the cortex of the cerebellum. And so that's why you can focus your eyes. That's why you can chew. That's why you can walk. That's why you can become a ballet dancer, or type without looking at the keyboard, or play a musical instrument. And you can see this information gets more and more complicated, but it's all the same principle. It's all a conditioned reflex storage of proprioceptive information in the cerebellar cortex. All right, and then there's a couple of others that I wanted to talk about in particular. There's, in the myotactic, there's 2 kinds. One is monosynaptic. It only involves 2 nerves, one from a sensory organ receptor, and the other one a motor nerve that goes back to usually a muscle of some kind. And that's what the patellar one is, or the equivalent one for the ankle is, or the one for the eye is. There's a blink reflex, the same way, that can be tested. And there's lots and lots of them, as I said, 9 basic ones. And then there's autonomic, that affect the inner organ. And so the physician can do the same kind of tests on organs that aren't associated with all of the stuff I was talking about. A common one is the tilt table. You lay down on a table and the physician tilts it quickly. And if you respond normally, what should happen is the sensors tell your internal system that something weird has happened to you, and your heart rate should go up and your blood pressure should go up. And so the physician actually measures those two things when he does the tilt. So you're all strapped in and ready to go. And then there's something a little surprising called the anal wink. You wouldn't think that that involves internal nerve system. And basically what it amounts to is if you stroke the area around the anal opening and everything is operating properly, the anal sphincter should close. And so that's a way to test all kinds of nerves, because a lot of them are involved and any one of them will prevent that from happening. And so that's a very important test on tumors, for example, in your lower intestinal tract. All of the nerves can be affected by something like colon cancer. And that's a way to do detection. It's not often done, but it can be done. And then, of course, we've got these polysynaptic that involve a lot of nerves. And in particular, a particular kind of nerve I haven't talked about called an interneuron. And I'm going to show you what all of this is about next. So reflexes are a simple arc where the signal never reaches the brain. It never goes up the spinal column. You've got a receptor. The sensory neuron passes the signal to the horn of the spinal column of that disc, just to the horn. The interneuron connects that sensory neuron with a motor neuron and sends an impulse down that motor neuron and makes a muscle or a gland or whatever's at the other end do its thing. And so interneurons relay information between sensor and motor neurons in the horn of the spinal disc. And after the fact, they can also send the signal to the brain so you know you moved. Because the movement itself is involuntary. It's non-conscious proprioception. Even your brain didn't have anything to do with it. You never thought about it. But you would like to know you moved, besides looking at your leg when the guy hit you with a hammer, right? You can learn about it that way, but the interneuron also sends a signal to your brain to let you know you moved, because there is proprioceptive information in this process. So the first one I'm going to talk about is, again, a very simple one. It's called the clasp knife reflex. And it's a protective mechanism against something called weightlifting failure. And it involves the Golgi tendon organ. And this is actually a very serious problem. I've spent a lot of time in the gym over the years in close proximity to very serious weightlifters and bodybuilders. And one of my favorite guys when I was living here in Milwaukee and going over to what is now 24-hour fitness was a bodybuilder who had won all sorts of titles. And I was watching him work out one day and he was doing curls. I don't know, you know what a curl is. You grab a weight and you bend your arm and you lift the weight that way. And he was really pushing himself. And all of a sudden he dropped the weight. And then he looked at his arm. And basically what had happened is the muscle, the tendon of the muscle had detached from the bone in his upper arm. And the muscle had just rolled up like a window shade and required some very, very, very serious surgery to put his arm back together again. So that's weightlifting failure. And this reflex is supposed to stop it from happening. But again, it's a non-conscious reflex. And you can consciously decide to override it when it says, I'm in pain, stop. And that's exactly what he did. He was pushing himself too hard. And it's actually not an uncommon one, although the injury he suffered was much more serious than normal. You always hear about athletes getting muscle tears. This is what it's from. Because the whole muscle doesn't have to detach, just some of the muscle fibers that are connected by some of the tendons to the bone can be torn before it becomes too serious an injury. And that's usually what is happening to everybody, runners and all kinds of people that play sports. In any event, what's supposed to happen is the Golgi tendon organ determines that there's too much tension in the tendon, and it sends an inhibitory signal right away through this very simple loop. You've got the receptor sending the signal to the horn. The horn goes through an interneuron, and in this case, the interneuron sends two signals. It sends a signal for one of the muscles in the arm to stop moving and tightening, and it sends another one to the other muscle in the arm to relax. And so basically the whole arm relaxes again, because you've got a biceps, and on the other side of the arm, you got a triceps, and you got to deal with both of them. But all of that happens in an instant when the tendon knows, or if you do something stupid, like you try to lift too fast. Remember, the Golgi tendon organ also detects velocity of change in addition to just length. And so that's usually the signal that goes through this arc, the velocity of change. All right, then we've got what we were calling the myotactic reflex. And here's the patellar reflex. So you've got a muscle spindle, and you tap on the patellar ligament, and that excites the nerve ending of the muscle spindle in the quadriceps at the top of the leg. That sends a signal through the dorsal root ganglion, and it goes into the horn. And then all kinds of things happen that are much more complex than before. Again, you've got to do two different signals. You've got to signal the quadriceps to stop, and you've got to signal the hamstring to do its thing as well. And so you've got all of this information being transferred from one simple nerve going in to all of the appropriate places going out to the muscles, and it's all being done by the interneuron switches in the horn. It never goes into the spinal column, and it never gets to the brain. And I'll bet you didn't know that that's how it worked. And then here we have the hot stove reflex, or the response to some kind of stimulus, like burning your finger or stepping on a tack. And now this one gets even more complicated because it involves a lot more nerves. And so you've got a whole bunch of different components of this reflex arc. But this whole idea is the same. You've got signal going in, pain, pain, pain. It gets there, and somehow the interneuron knows not even to bother sending it up the spinal column, it's got to react even faster than that. And so its integrating center does all of the effector signals going back to the muscles to get out of the way in a hurry. And in this case, the muscle contracts and the triceps extends. And so you've got the muscle doing two different muscles doing two different things pretty much instantly, all in that integrating center within the disc. All right, and now I wanted to talk just a little bit about balance and what balance is all about, because balance is basically a reflex, a much more complicated one. And in this case, there are four basic components involved in keeping our balance. We've got the vestibular system, and it's in the inner ear, right next to the hearing mechanism in the ear. And in fact, the vestibular system uses the same endolymph, the fluid, special fluid, that's responsible for providing the signals from the inner ear to the brain that are what we call hearing. But it's used in a very different way, but it's actually shared through a membrane. All right, and unlike what most people think, the semicircular canals basically only detect rotational motion, and in particular acceleration in that rotational motion. So they're usually not very much involved in most of our responses to what as what we call balance. It's actually two things that nobody talks about. There are little sacs called a utricle and a saccule, and they're the ones that have the receptors in them that detect, in the case of the utricle, up and down motion, tilting our head forward and back, or in the case of the saccule, side to side motion. And so it's the utricle which is actually most important out of the vestibular system for our sense of balance. And in the utricle are hairs, just like the microcelia hairs associated with the inner ear that are associated with hearing. But in this case, they operate differently. And there are things called otoliths involved, these little pieces of limestone, basically, that are floating in endolymph above these hairs. And when you move your head up and down, what's supposed to happen is the hairs move on their base, but it takes the otoliths a while to catch up. And it's that change in the difference in velocities between those two that the vestibular system detects. And what usually happens when people lose balance, especially in old age, is replacing those stones gets lost in the process. Either we don't make the limestone fast enough, or we don't put it in the right place. And so that's the part of the system that breaks down when we have no sense of balance as we get older, or we start losing our sense of balance. That's the part of the system that doesn't work as well as it should. Semicircular canals are there, but they're no big deal. They're involved in our understanding of upright, and there's three of them, basically going off in the three Cartesian coordinate directions, if you wish, up, down, and sideways, or left, right, and up, or whatever you want to call it. In any event, reflexes just in the head associated with the vestibular system happen very early. Infants learn to lift their heads while lying on their stomachs. That's a proprioceptive response. And basically the vestibular system detects non-vertical orientation of the head and starts feeding that information of movement to the cerebellum of the infant. And that gets stored, and the infant learns to lift its head basically as a reflex. And that develops in newborns, usually before they're 2 months old, and generally not after they're 3 months old. If that reflex doesn't develop in that by that time, then the pediatrician knows something's going on. The visual system gets involved as well. And it provides orientation relative to the horizon. It creates what's called an allocentric reference frame, an internal reference frame based on objects in the environment. Now that's allocentric external reference frame based on objects in the environment. You got to remember what my prefixes mean. All right, so that's a very useful thing. If you know anything about rotation, what dancers do, dancers don't let their heads turn at the same time they do. Ditto with ice skaters who are in a spin. They try to keep their eyes focused, and then they snap their heads around at the end of the spin to reorient themselves, right? And so that's a very different kind of cue to the rest of our system. And the infants develop what's called a head writing reflex very early, and that's associated with the eyes. And that lets the pediatrician knows that that part of the infant is developing its nerves properly. So basically the infant is held straight up and then its head is tilted. And the infant knows how to move its head up and back because that already got developed in head writing. And so it uses optical inputs in association with the vestibular system to restore its head to a vertical position. And so now the vestibular and the visual systems are working together. And that kind of a reflex develops in infants usually sometime after 2 or 3 months, but not very much after. And again, that's a standard test that pediatricians do to look at nerve development in the head and neck for that matter. All right, and then for real balance, not just tilting our head or moving our head, the proprioceptive system comes into play, and it stores information on the movement of neck muscles in the cerebellum, right? Mostly neck muscles in balance, because really our whole frame of reference is coming from the visual system through that allocentric reference. And then, of course, the cerebellum, which initiates non-conscious muscle movement, gets involved, coordinates all the information from the other 3 systems, and says it's time to tilt our head back to vertical. Or in the case of more complicated balance, like we're standing up, or a football player gets knocked over a little bit from a partial tackle, the whole body gets straightened out. And so that's a writing reflex. That's a very complex non-conscious movement. That's when the whole body is taken out of its normal standing position. So we still have the vestibular system involved. We still have the visual system creating that allocentric reference. And those 2 systems combine to start the muscle movement to tilt our head back to vertical. So that's the first part of the body that moves. And it moves because of the simple reflexes that don't involve the cerebellum or other part of the brain at all. That all happens in that simple reflex arc. And then, surprise, surprise, we have touch receptors in the soles of our feet. They're basically pressure receptors, and they can actually detect a difference in the pressure over the surface, the bottom surface of our foot, even if it's in a shoe. And now the cerebellum gets into play, and it takes all of the information from that combined visual system and from the touch receptors in the foot. It combines all of those inputs and creates an internal image of our current posture. I'm leaning to the left, or I'm falling backwards, or whatever it happens to be. And it compares that perceived posture with what it expects as a normal posture. I should be standing straight up. I don't normally tilt to the left or fall backwards. And then it uses an iterative process. It non-consciously starts all of the muscle movements to move our abnormal posture towards the normal posture. And it basically does it quickly and grossly, and then uses an iterative process of information coming from all of these systems up to the cerebellum and back to the muscles until it gets it right. And we're standing exactly the way we're supposed to be. So that's really complicated, but again, we're not making any conscious decisions. All of that happens, and it happens fast. And it happens faster in some people than in others for whatever reasons in terms of how well their cerebellum works. All right, and so that's basically the end of what I was going to talk about this time. And I don't know how well I've done on time, but I hope it's not much more than an hour. And just as a preview for what I'm going to talk about in part 3, I'm going to talk about movement. And movement involves the motor cortex, the descending nerve pathways, the ones going back to the muscle, and the differences and combinations of conscious and non-conscious movement. I want to move my leg is moving, how do I stop it, for example? Or a combination thereof, because all of that coordinated iterative process, that involves both conscious and non-conscious, even though the conscious part is done non-consciously, because that's where the motor information is stored. And so that's what I meant by non-conscious, conscious movement. All right, and then I'm going to talk about the details of balance. So I'm going to actually talk about how those vestibular parts work as mechanoreceptors, which is basically what they are. And then I'm going to talk about assessment of balance, because that involves how you do tests for all of these nerve tracts that I was talking about. I'm going to talk about the various kinds of problems we can have with balance, because we're all getting old and that's going to be relevant sooner or later. And then I'm going to talk about training, which is how I got involved in all of this in the first place. And hopefully I've got enough time to tell a story. I worked with Oregon Health and Sciences in their patents and licensing department. And one day a guy from Legacy, who's not really a part of it or wasn't at the time, came over to talk to me because Legacy didn't have its own patent and licensing. And he had invented a machine to train people who had had strokes. And usually what happens in a stroke is one side of your body doesn't work. And so he had developed a machine that would automatically, he thought, train a person's leg to start working by moving that leg in such a way that it produced proprioceptive information that could be stored in the cerebellum, and in the process using alternative nerve pathways, because there are multiple pathways in all of these places that do exactly the same thing. He thought he could teach people to work without, say, dragging a leg or something like that. And so the first thing I had to do was ask him, how the hell is it supposed to work? Sounds like magic. And then all of a sudden he started telling me this story, not in any great detail, but he started telling me stories about muscle spindles and saying muscle spindles are at the heart of this. Well, he wasn't a neurologist either, and he didn't have a clue what a muscle spindle was, but he knew that muscle spindles were at the heart of what he was trying to do by retraining muscles. Right? And that got me started. What the hell's a muscle spindle? How does it work? And one thing led to another, and now you've seen the result, God forbid. So anyhow, that's how, as I mentioned, that's how I get into most things. Somebody says something that piques my curiosity, and I sort of take it from there and get curious and want to know more, whether it's Dick Pugh telling me what a meteorite was, or somebody else showing me a gem and telling me where it's found or what it's made of, or somebody else doing this kind of thing. And so finally, I'm going to talk about the last part of non-conscious proprioception, which is the visceral system. And the visceral system is a system all unto itself. It has its own receptors. Remember, this is an internal system that controls our organs, like our heart and like our kidneys. And it has receptors of all different kinds all over the body. And it's got a separate nerve system that receives information from those nerves and then sends information, not to muscles usually, but to some internal organ to tell it to turn up this or turn down that, because your heart's beating too fast or your blood pressure is too low or something like that. And so that's how the body regulates its body functions. And finally, I'm going to talk about a bunch of examples, some of which are exceedingly complex and therefore very surprising, that that's how our body internally actually works. And all of that is done non-consciously. And so a lot of it's got the same principles. It just uses different kinds of receptors and different kinds of nerves, and usually doesn't involve muscles, unless we're talking about the heart and the heart rate, and then it does involve a heart muscle. But surprisingly, the heart muscle doesn't work the way our skeletal muscles do. It's controlled electrically. It doesn't have muscle spindles. And so that's a whole different process, which is why the visceral system's parasympathetic nerves can work on it. Anyhow, that's what I'm going to talk about next time, but hopefully not for at least 3 or 4 weeks. However, if Don, you're still there, sometime towards the end of the month, I would like to give another gem talk. And this time I'd like to give one on zircon. And I'm going to approach the talk from a totally different perspective than the geology kind of talk I gave when I talked about beryl minerals, which is why I would like to do it before all of the information and impressions from the beryl talk sort of fade away into the darkness. Anyhow,
you can find those on
I'm gonna stop sharing the slides somehow. Hopefully there I show up again, and lots more people than I expected to still have stuck with it. And it actually was a lot better than most of the talks I give, as far as the length is concerned, at least. And so
I do have to go, but it was really fabulous, fascinating, and I will see you next time.
All right.
Thank you so much.
Glad you could join us, Barb.
Oh, me too. What a pleasure. Bye-bye.
So next week, next Wednesday, Todd Duncan from Portland Community College Astronomy or is going to be talking on
He is from Pacific University. He's a astrophysicist from Pacific University in Forest Grove.
oh, I thought he was in Portland Community College in well, okay, good to know.
Rose City Astronomers, and he,
It's going to be experiencing the universe toward a science of mindful participation in nature. That's the title of his talk next week. So
he's quite a fascinating speaker, and he sent, I'm sure Donald forwarded a video of.
we'll have a YouTube of him on the announcement. And thank you very much, Steve. It's very enlightening. And Dave, you want to hang up the recorder?
Well, I got kicked off and now I don't have permission to do that anymore, but you could do that, I think.
Okay, what do I do?
That's
Just-
not the end of the world.
Up where it says, let's see, up where it says recording in the top left, is
Yeah.
there a selection there for you to stop?